This is the Tesla 2170 lithium-ion battery cell. 2,976 of these cells form the standard range battery pack on their Model 3 electric vehicle. The 2170 cell was created as an evolution of the popular 18650 cell to fulfill the technical requirements of their newer electric vehicle designs. Touted as the highest energy density cell in the world, it effectively doubled the storage capacity and current delivery of the Panasonic 18650 cells used in their existing vehicles, while simultaneously reducing production costs. Unassumingly named by their dimensions, both the 2170 and 18650 battery cells, along with a myriad of new, thin, bar-shaped configurations known as prismatic cells, all share a common distinction. These high-capacity lithium-ion battery cell technologies all represent the first hopeful steps in transitioning society towards a new standard in practical and economical transportation via electric vehicles. While the electrochemical battery has been around for well over 200 years, using them practically in vehicles in a manner that could be considered competitive with petroleum-based fuels and natural gas has been an incredible challenge. It's only within the last 20 years of innovation that the concept has finally become feasible. The modern incarnation of the electrochemical battery is credited to the Italian scientist Alessandro Volta, who put together the first battery in response to the misguided findings of his colleague Luigi Galvani. In 1780, Galvani had shown that the legs of frogs hanging on brass hooks would twitch when touched with a probe made from a dissimilar metal. He believed that this was caused by electricity from within the frog's tissues and called it animal electricity. Volta suspected that the electric current came from the two dissimilar metals and it was being transmitted through the frog's tissues, not originating from it. He experimented with stacks of alternating plates of silver and zinc separated by cloth soaked in salt water, and found that an electric current did, in fact, flow through a wire applied to both ends of the pile. Volta had developed the first electrochemical battery known as a voltaic pile. Each pair of silver and zinc formed the electrode of a voltaic or galvanic cell. The zinc plate would react with the salt water, producing an accumulation of electrons. An electrode that results in the production of electrons is known as an anode. Meanwhile, at the silver plate, a simultaneous reaction with the salt water occurred, enabling it to accept electrons. This is known as a cathode. The chemical that both electrodes react with, in this case salt water, is known as an electrolyte. The electrolyte also functions as a pathway for the transfer of positively charged ions to balance the flow of electrons from the anode to the cathode, keeping the reaction running. In order to prevent the ions of the more noble metal from plating out the other electrode, a semi-permeable membrane is sometimes used to divide the reaction halves within the electrolyte. This type of chemical reaction is known as a reduction-oxidation reaction or a redox reaction. The entire reaction can be split into two half reactions, and in the case of an electrochemical cell, one half reaction occurs at the anode, while the other at the cathode. Each of these reactions possesses a particular standard potential or a relative ability to either produce or absorb electrons. The difference in standard potential between the electrodes becomes the cell's overall electrochemical potential or its voltage. The greater this difference, the greater the electrochemical potential and the higher the cell's voltage. Individual cells can be combined into configurations that can both increase the total voltage and current capacity. This is known as a battery. On primary batteries, the electrodes become depleted as they release their positive or negative ions into the electrolyte, or the buildup of reaction products on the electrodes prevent the reaction from continuing. This results in a one-time use battery. In secondary batteries, the chemical reaction that occurred during the discharge can be reversed. However, the process isn't perfect as each charge cycle causes the battery to lose performance over time, with each battery chemistry having its own particular mechanism of wear. This is exacerbated when a battery is discharged and recharged in a highly frequent manner. Beyond the advent of the voltaic pile, batteries took on more practical forms with various configurations and chemistries being developed thereafter. However, all were primary batteries and would be permanently drained when the chemical reactions were spent. In 1859, the French physicist Gaston Plante would invent the lead-acid battery, the first ever battery that could be recharged. A lead-acid cell consists of a lead anode and a lead dioxide cathode, immersed in a sulfuric acid electrolyte. While discharging, both electrodes react with the sulfuric acid to produce lead sulfate while the electrolyte loses its dissolved sulfuric acid. But what made this discovery so important was that these chemical reactions could be reversed by passing a reverse current through the battery, recharging it. By the 1880s, the lead-acid battery would take on a more practical form, with each cell consisting of interlaced plates of lead and lead dioxide. This multi-plate design made lead-acid batteries far easier to mass-produce, as well as allow the cells to be stacked easily for different application requirements. Because the electrodes and electrolytes within a battery aren't 100% conductive, they all inherently have internal resistance. Lead-acid batteries by nature have low internal resistance, making them ideal for producing large surges of current. This property made them ideal for powering large, current-intensive loads such as electric motors. By the end of the 1880s, the lead-acid battery brought about the rise of the first electric vehicles in Europe. Before the proliferation of the internal combustion engine, electric automobiles held many speed and distance records. Among the most notable of these records were the breaking of the 100 km/h speed barrier by Camille Ganassi on April 29, 1899, in his rocket-shaped vehicle La Jamais Contente. In the early 1900s, the electric vehicle began to grow in popularity in the United States after thriving in Europe for over 15 years. By 1905 in the United States, 40% of automobiles were powered by steam, 38% by electricity, and only 22% by gasoline. However, the first golden age of electric vehicles would soon end as gasoline-enabled vehicles to travel further and at higher speeds. The lack of sufficient electric infrastructure for recharging batteries would also hinder adoption. Henry Ford's mass-produced Model T was the final blow to the electric car. Introduced in 1908, the Model T made gasoline-powered cars widely available and affordable. By 1910, a gasoline-powered car could be purchased for as low as $650. This was less than half the cost of many electric vehicles at the time. Within a few years, most electric vehicle manufacturers had ceased production. Most early electric vehicles had a top speed well below 30 km/h or about 18 mph and generally had a range of about 40 km or about 24 miles at best. Despite these limitations, the lead-acid battery would still remain a part of the automotive industry as their high current capacity made them ideal for powering electric starters on gasoline and diesel engines. Making their first production appearance on several Cadillac vehicles in 1912, the lead-acid battery would evolve with vehicle designs over the next century, becoming a key part of their electromechanical and electronic systems, particularly on heavily computerized vehicles of today. Even 150 years later, the lead-acid battery still retains a significant market share due to the lack of any cost-effective alternatives for internal combustion-powered vehicles' electric systems and other durable, short-cycled, high-demand use cases. The energy storage characteristics of a battery's chemistry can be compared with a handful of key parameters. Specific energy is the amount of energy it can store per mass unit, energy density specifies the amount of energy it can store per unit of volume, and specific power quantifies how much power it can generate per unit of mass. Other parameters that determine a battery's suitability for an application include its self-discharge rate, typically measured in % of charge loss per month, its charge-recharge cycle durability, charge-recharge energy efficiency, nominal cell voltage, and cost per unit of energy. A typical modern AA alkaline primary battery, for example, when compared to a lead-acid cell, has almost 4.5 times the specific energy, 5.5 times the energy density, but only 1/3 the specific power. They also have incredibly low self-discharge rates, losing only about 0.17% per month, as opposed to the 3 to 20% for a lead-acid cell. Where a lead-acid battery stands out compared to other more superior chemistries is in cost. A lead-acid battery can store almost 40 times more energy per dollar than the more energy-dense AA battery. Over the next 60 years, the electric vehicle entered a dark period with little advancement in technology. Cheap, abundant gasoline and continued improvement of the internal combustion engine hampered demand for alternative fuel vehicles. However, in the United States, during the early 1970s, soaring oil prices and gasoline shortages piqued some interest in electric vehicles once again, though the enthusiasm was short-lived. The initiative did yield some research and development as well as a few experimental fleet vehicle programs. It should be noted that it was during this period in history the most famous electric vehicle to date, the Lunar Lander, made its first drive on the moon in 1971. Though it helped raise the profile of electric vehicles, from a technical standpoint, it operated on 2 silver oxide primary batteries, offering little in crossover technology to its terrestrial counterpart. Fundamentally, little had changed in battery technology since the first golden age of electric vehicles, still limiting their speed and range to non-competitive levels. In the late 1960s, research had begun by the global communications company ComSat on a relatively new battery chemistry called nickel hydrogen. Designed specifically for use on satellites, probes, and other space vehicles, these batteries used hydrogen stored at up to 82 bar with a nickel oxide hydroxide cathode and a platinum-based catalyst anode that behaved similar to a hydrogen fuel cell. The electrolyte used was an alkaline chemical, potassium hydroxide. As the battery discharges, the hydrogen is consumed by the anode, producing water, which is simultaneously consumed in the nickel electrodes reaction. The pressure of the hydrogen would decrease as the cell is depleted, offering a reliable indicator of the battery's charge. Though nickel-hydrogen batteries offered only a slightly better energy storage capacity than lead-acid batteries, their service life exceeded 15 years, and they had a cycle durability exceeding 20,000 charge-recharge cycles. They were also very resilient to overcharging and overheating. By the early 1980s, their use on space vehicles became common, appearing on several notable missions such as the Mercury Messenger, Mars Odyssey, Mars Global Surveyor, the Hubble Space Telescope, and even the International Space Station. Nickel-hydrogen cell chemistry was based on nickel-cadmium, one of the first rechargeable alkaline cell chemistries ever developed. First created by Valdemar Junger of Sweden in 1899, nickel-cadmium cells also used a nickel oxide hydroxide cathode with a potassium hydroxide electrolyte, though they used the toxic heavy metal cadmium as an anode. Though this offered slightly better energy density and specific power than lead-acid cells, they offered almost 6 times the cycle durability, making them ideal for consumer products use. Rechargeable nickel-cadmium batteries could be found powering early portable power tools, photography equipment, flashlights, emergency lighting, toys, and portable electronic devices. Their higher cost and lackluster energy capacity, as well as their relatively more complex charging requirements, made them less than ideal for electric vehicle use. They also suffer from memory effect, a condition in which a battery gradually loses its maximum energy capacity if they're repeatedly recharged after being only partially discharged. As work was being done on nickel-hydrogen batteries, simultaneously a less bulky method for storing hydrogen was being explored at the Batali Geneva Research Center. Known as nickel metal hydride, this new chemistry relied on metal hydrides, a class of materials containing metal or metalloid bonded to hydrogen to function as an anode. Over the next 2 decades, research into nickel metal hydride cell technology was supported heavily by both Daimler-Benz and by Volkswagen Audi Group, resulting in the first generation of batteries achieving storage capacities similar to nickel hydrogen, though with a 5-fold increase in specific power. However, these suffered from electrode alloy instability within the alkaline electrolyte and consequently suffered from low charge cycle durability, typically around 500 cycles. Finally, in 1987, a breakthrough in research led to an anode material composed of a mixture of lanthanum, neodymium, nickel, cobalt, and silicon that allowed the cell to retain 84% of its charge capacity after 4,000 charge-recharge cycles. This breakthrough led to the first consumer-grade nickel metal hydride batteries to become commercially available in 1989. By the late 1990s, more advanced alloys consisting of titanium and nickel, modified with chromium, cobalt, and manganese, would result in specific energies almost 2.5 times higher than that of lead-acid cells. These new anode materials also offered energy densities 5.5 times greater, and with their already drastically improved specific power, for the first time in automotive history, a battery technology had emerged as a viable successor to the lead-acid battery. Nickel metal hydride batteries did suffer from some drawbacks, such as having a higher self-discharge rate than lead-acid batteries, memory effect issues, and costs as high as 2 to 3 times more per kilowatt-hour when compared to lead-acid. Though with the emergence of inexpensive embedded microprocessors, advanced charging and battery monitor techniques could mitigate many of these chemistry issues. Nickel metal hydride became widely popular in the consumer space, quickly replacing nickel-cadmium and enabling a new surge in high-consumption mobile electronics. Ultra-low self-discharge variants would eventually be developed in 2005 for the consumer market, further increasing their appeal. Almost 100 years after the first golden age of electric vehicles, a confluence of several factors reignited interest in electric vehicles once again. In the early 1990s, the California Air Resources Board, or CARB, began a push for more fuel-efficient, lower-emissions vehicles with the ultimate goal of transitioning to zero-emission vehicles. This initiative intersected with the recent refinement of nickel metal hydride battery technology, making practical electric vehicles a viable commercial option to pursue. By the late 1990s, mass-market electric vehicle production had started once again. Taking a more risk-averse approach, many automakers started to develop all-electric models based on existing platforms in their model lineup. Some notable all-electric vehicles were the Toyota RAV4, Honda EV Plus hatchback, Ford Ranger EV, S10 EV pickup, and the controversial GM EV1. While other battery chemistries were explored, these first-generation modern electric vehicles all predominantly used nickel metal hydride batteries in their powertrains. Due to the limitations of the vehicle size and target price point, most of these vehicles employed battery pack sizes of around 30 kilowatt hours. This was sufficient enough to allow these early vehicles to operate at highway speeds comfortably, with ranges of around 160 kilometers or about 100 miles. For the first time, electric vehicles were now a practical option for use outside of cities, making all-electric suburban commuting possible. While these early vehicles proved to be popular in niche markets such as short-distance urban use and fleet vehicles, they still lacked mass market appeal due to their image of being slow, low-powered, expensive, and range-limited. In the United States, lower gas prices and higher profit margins left them mostly ignored in favor of larger truck-based vehicles. It would take further advancement for them to even be seen as a competitive product by the majority of the automotive market. During the mid-1970s, just after the peak of the energy crisis, in an attempt to challenge Bell Labs and its image of innovation, ExxonMobil began to back a breakthrough made by English chemist Stanley Whittingham. Whittingham had discovered a way to make an electrode from a layer material that could store lithium ions within sheets of titanium sulfide. The lithium ions could be moved from one electrode to the other, creating a battery from the highly reactive properties of lithium itself. In lithium-based cells, the electrolyte does not take part in the reaction, but rather mediate the movement of ions, controlling the cell's characteristics. The method developed by Whittingham was known as intercalation, and it permitted the addition of lithium ions into a host material without significantly changing its structure. Because metallic lithium was used as the anode, the first variants of lithium-based batteries were known as lithium metal batteries. Compared to other battery chemistries, they have incredibly high energy densities, with some as high as 10 times that of lead-acid cells. They also have self-discharge rates well below 1% per month, as well as long shelf life, easily surpassing a decade. Whittingham's initial use of titanium disulfide had proven to be impractical. Its raw form cost over $1,000 per kilogram in the 1970s, and it also required a complex and costly synthesis process. Furthermore, when exposed to air, titanium disulfide reacts to form hydrogen sulfide compounds, which have an unpleasant odor and are toxic to most animals. The experimental cells were also dangerous, as pure lithium will instantly react with water or even moisture in the air, releasing flammable hydrogen gas. By the late 1970s, newer cathode materials would result in the first consumer lithium metal primary batteries. These tend to be found in low-power consumer electronics, medical devices, and on computer equipment where long life and high energy densities are needed. Most of these new lithium cells found in consumer applications used manganese dioxide as a cathode, with a salt of lithium dissolved in an organic solvent as an electrolyte. Despite the advantages offered by lithium, a practical rechargeable lithium-ion battery still remained a challenge. The electrochemical reaction that enabled lithium cells to function so effectively also made them prone to ignition when overcharged. The cathode would also quickly erode from repeated charge and discharge cycles. The problems of Whittingham's lithium cell would soon be solved by American material scientist and solid-state physicist John B. Goodenough. Goodenough had become very familiar with a family of compounds known as metal oxides. These compounds combined oxygen and a variety of metal elements. He proposed that metal oxides would allow for charging and discharging at a higher voltage than Whittingham's cells, which would result in both greater energy storage as well as less volatility. Goodenough's team experimented with several metal oxides and had concluded that cobalt was the most stable, allowing lithium ions to be extracted at up to 4 volts without eroding the electrodes. Completed in 1980, the lithium cobalt oxide cathode-based lithium-ion cell became a massive breakthrough. The world's first rechargeable lithium-ion battery had an energy density unmatched by anything else yet seen, offering a specific energy and an energy density almost 7 times that of lead-acid. Because lithium cobalt oxide was such a stable positive electrode material, it could be used with a negative electrode material other than lithium metal. In that same year, Moroccan engineer Rashid Yazami demonstrated the reversible electrochemical intercalation of lithium in graphite, inventing the far safer and more stable lithium graphite anode, eliminating the need for pure metallic lithium. During recharging, when a voltage is applied, the positively charged lithium ions from the cathode migrate to the graphite anode and become lithium metal. Because lithium has a strong electrochemical driving force to be oxidized, upon discharging, it migrates back to the cathode, becoming a positive lithium ion again while giving up its electron to the cobalt. In 1991, Sony combined Goodenough's cathode and a carbon anode into the world's first commercial rechargeable lithium-ion battery. The results were a huge commercial success, not only in battery sales, but also via the abundance of consumer electronic products that could now be produced. The lithium-ion battery solved one of Sony's biggest technical obstacles, powering its leading electronic product, handheld video cameras, making them a huge seller. Though lithium cobalt oxide cells have a high capacity, their more reactive nature made them susceptible to thermal runaway when overcharged or physically damaged. This susceptibility to explosion and fire made them unsuitable for large capacity mobile use. By the late 1990s, Goodenough once again made a huge leap in battery technology by introducing a far more stable lithium-ion cathode based on lithium, iron, and phosphate. This cathode material was thermally stable and it allowed the formation of crystalline lithium ferrophosphate structures that permitted ions more pathways to move in and out of the material. These classes of cathodes, called phosphoolivines, possess a similar structure as mineral olivine, a magnesium iron silicate that is a primary component of the Earth's upper mantle. Lithium ferrophosphates came as the successor to a similar group of cathodes made from manganese spinel, which also utilized a crystal structure to improve thermal stability. While effective, they suffer from poor cycling stability due to the tendency of manganese to dissolve in the electrolyte. They also weren't as thermally stable as lithium ferrophosphates, though they were cheaper to construct due to the relative low cost of manganese. Lithium-ion cells can now be made safely into large formats that could undergo rapid charge-discharge cycles. This new cathode material finally opened up lithium-ion batteries to new high-demand applications, from power tools to hybrid and electric vehicles. In December of 1997, at the Los Angeles International Auto Show, Nissan introduced the Ultra EV. Aside from its peculiar design that fused a sedan with a minivan, it possessed another unique characteristic. It was the first commercial electric vehicle to use lithium-ion batteries in its powertrain. Though it only sold 200 units, primarily for fleet use, its 33 kilowatt-hour battery pack, which weighed 360 kilograms or around 800 pounds, could power it comfortably to a range of around 200 kilometers or about 125 miles. Despite lithium-ion batteries becoming a viable option for electric cars, the second half of the 1990s into the mid-2000s were primarily dominated by the more risk-averse technology of hybrid-powered vehicles. And even these successful early models, such as the Toyota Prius and the Honda Insight, were generally still powered by nickel-metal hydride battery technology. At the time, lithium-ion batteries were still relatively unproven for vehicle use, and also cost more per kilowatt-hour. It would take a small Silicon Valley startup, Tesla Motors, starting with their announcement of producing a luxury electric sports car that could go more than 200 miles on a single charge, to ignite momentum for the broader consumer appeal of electric vehicles. By 2010, Tesla would grow to establish a manufacturing facility in California, winning wide acclaim for its cars and becoming the largest auto industry employer in California. Their success spurred many large automakers to accelerate work on their own electric vehicles. By 2020, virtually every major manufacturer has some form of all-electric vehicle offering among their product line. The vast majority achieve ranges between 160 kilometers to 320 kilometers or 100 to 200 miles, with recharge times from 4 to 8 hours. Some more advanced models, such as Tesla's long-range Model 3, can even match or exceed the range of gasoline engines, achieving over 600 kilometers or 380 miles. Around 2010, the cathode material of lithium-ion cells would once again evolve with the advent of lithium nickel manganese cobalt oxide cathodes, or NMC. NMC cells also has the lowest self-heating rate out of the different types of lithium-ion cells. They're currently in high demand and have been used by almost every major electric vehicle manufacturer. Curiously, Tesla is known for being the only manufacturer who does not use NMC cell technology, but rather much older lithium nickel cobalt aluminum oxide cathode, or NCA. NCA cells have been around since 1999 for special applications. It shares similarities with NMC by offering high specific energy and specific power with a longer lifespan. However, NCA batteries are not as safe, requiring special safety monitoring measures to be employed for use in electric vehicles. Tesla claims that using them is more cost-effective due to the lower cobalt content. With the surge in consumer adoption of electric vehicles comes a rise in the demand for the lithium-ion batteries that power them. And with this demand comes a hidden economic force that could potentially derail this momentum. These batteries all rely on two key raw materials, lithium and cobalt, both of which are relatively scarce in supply on the world stage. Economic forecasts have suggested that the worldwide supply of lithium and cobalt could become critical by 2050. Cobalt supplies in particular are even more vulnerable as worldwide demand is expected to be twice the current worldwide supply within 20 years. While roughly half of the cobalt produced is currently used for batteries, the metal also has important uses in electronics, tooling, and superalloys like those used in jet turbines. More than half of the world's cobalt comes from the Democratic Republic of the Congo, which the USGS describes as having a high risk of doing business and suffers from a substantial risk of civil war. With no state regulation, cobalt mining in the region is also plagued with exploitative practices such as child and forced labor, as well as environmental disregard. Raw materials are generally funneled through independent purchasers through China, making the true human costs of these materials hidden. Research into technologies that could solve this dilemma are already underway, from short-term solutions such as battery recycling to the recent race to discover new chemistries that remove cobalt from lithium-ion batteries. The industry as a whole is beginning to aggressively pursue solutions. Though even with these efforts, some have speculated that there simply isn't enough cobalt in the world to keep up with the pace of advancement. It may take the fulfillment of the next generation of technologies, such as solid-state batteries, to truly make the electric vehicle as prolific as the internal combustion engine.